Okay, to wrap up our review of the material we've been covering, we want to review where we're at in section 8.4. And there's two tests that are in this section, and remember, at this point here, these are just tests for convergence. / divergence. These won't tell me anything about what the series actually converges to. Alright, so the first one we had here after we did a little bit of investigating with some examples was the divergence theorem. And remember, the key thing here is that the name tells us we only apply this to determine that a series diverges. You can never use this to say that a series converges. So basically it says if the series sum of a sub k has the limit as k goes to infinity of a sub k not desktop there not equal to 0, then the series diverges. Alright, so that's what it did there. And we did a couple examples of this, but just to kind of refresh you a little bit here, and we're going to put up an example here that we did at the end of Wednesday's class to kind of see what we need to do here for the remaining test, is that if we have, for instance, k equals 1 to infinity of 2k plus 1 over 3k minus 2, we can use the divergence test on this, because if I look at what the limit as k goes to infinity of 2k plus 1 is over 3k minus 2, well, this is the limit as k goes to infinity of 2k over 3k, which, speeding it up a little bit here, that's just equal to 2/3. But since the limit as k goes to infinity of a sub k does not equal 0, we can conclude that this series diverges. We can conclude that the series diverges, which then we're done. It diverges. Now the other example we had looked at, and I'm going to put it up here again because we're going to examine in this example in more detail. It's a very famous example. This is where people mess up the divergence test. Whoops. If we look at the series from k equals 1 to infinity of 1 over k, well, we have the limit as k goes to infinity of 1 over k equaling 0. But what we have here is that the divergence test is inconclusive. Or sometimes I say tells us nothing. That just does not give me enough information. And as I said in the other video at the end of it, this series diverges, which might go against your initial thought, because if you look at what this is 1 plus 1/2 plus 1/3 plus 1/4, and you're like, well, I keep adding smaller numbers. Well, yeah, you do, but it still goes off to infinity, which is a very interesting example. But let's go and see how we can actually show that that does diverge. So to show how this does diverge, we need another test, and this is the integral test. So there's a couple things that we need here. We first need suppose f at x is a decreasing function for x greater than or equal to 1, and let a sub k equal f at k for k equals 1, 2, 3. Then the conclusion is that the series from k equals 1 to infinity and the improper integral from 1 to infinity both converge or diverge. So what does that mean here? It means if we can do an integral and get that the integral converges, then we get that the series also converges. Now, the way this is worded, it makes it sound like, oh, it's going to be hard to figure out what this f at x is, and a sub k equaling f sub k, or whatever this is here. This is actually really easy. All we're doing is whatever the equation is here for a sub k, we're going to integrate that. Whatever the expression is for a sub k is, we're going to do an improper integral of it. And if that improper integral converges, then the series converges. If the improper integral diverges, the series diverges. So let's apply the test on this first example, and then we'll see why it works. We'll talk about why it works. So let's look at apply the integral test to this series. Okay, so as I said, what we're going to do here is we're just going to simply say, okay, well, evaluate the integral from 1 to infinity of 1 over x dx. We're literally just integrating the exact same expression, except I force of habit make it x instead of, I mean, you could write k dk if you wanted to, but force of habit I just convert it back to x. Alright, so then we just evaluate this. Now, we did this in the previous chapter, so this would be the limit as b goes to infinity, the integral from 1 to b of 1 over x dx, which would equal the limit as b goes to infinity of the natural log of x evaluated from 1 to b, which would be the limit as b goes to infinity. These are all positive numbers, so I can really just drop the absolute value. So the natural log of b minus the natural log of 1. Natural log of 1 is 0. That goes to 0. But then we have to think of what does the natural log go to as you go to infinity. I know we've talked about this before in this class, but it's something you should already know. This actually goes to infinity. So the integral diverges. So this integral that I did diverges, but then I'm going to scroll back up here. My integral test says that if I can do an integral, then the integral and the series either both converge or they both diverge. So since this integral diverges, we can conclude that the series diverges. So now we have shown, using the integral test, that this series of 1 to infinity diverges. So let's look at why the integral test actually works here. So we're actually going to go ahead and prove this a little bit here. So what we're going to do here is we'll go ahead and do this simple case with this 1 over k. Well, we won't necessarily do 1 over k here. I'll do something here. We're going to look at the series from k equals, I'm going to start at 2 to infinity of a sub k, but I'm still going to do my integral from 1 to infinity. And I'm going to draw a picture of this, because the picture is going to really help us see here. So first off, f of x is decreasing. So it's going to look something like this, maybe. And then I'm going to go ahead and label some points here. So 1, 2, 3, 4, 5, 6. All right, so I'm going to go ahead and shade in and then erase. So, you know, the integral is this area right here, right? That's what the integral is. But then what I'm going to do here is go back to Calc 1 and do something that we probably wish we wouldn't have to do again, but it's actually going to help us here, is I'm going to do a Riemann sum. I'm going to use right endpoints of width 1 here. But if I look at here, these rectangles, this would be, the area of this would be A1, the area of this would be A2, A3, A4, and A5. In other words, the area of my rectangles is, oops, not 1, it starts at 2, because we're doing right endpoints. Starts at 2, goes off to infinity of a sub k. Okay, so then what do we have here? Well, the area under the curve, we know that the rectangles underestimate, just based off the picture, the area under the curve. We know that. So what do we know here? So then we know that k equals 2 to infinity of a sub k. I'll go ahead and say less than or equal, and you can just basically say less than, is less than or equal to the integral from 1 to infinity of f of x dx. Now, suppose integral converges to a number. Well, if that integral converges to a number, this has to be smaller. So wait, if this is converging to a number and this has to be smaller, and we have because the integral test here, what we aren't really clearly saying here is that you know, we have a series that has some monotonic properties and everything, but because this is bounded and goes to a number, converges to a number, this has to be smaller than that number, so it's also got to go to some number. So it also converges. Now we have to also consider the diverging cases. If the series diverges, let's say, to infinity, well then the integral is bigger, which it's weird to say it's bigger than infinity, but it's bigger, so it has to diverge to infinity. Now this is really only half the argument here. We do need to do another argument here to get it completely, and I'll draw the picture, but the argument is very similar. So that gets us kind of halfway to the proof. So we'll draw this again, but this time what we're going to do is we're going to compare the integral of 1 to infinity of f at x dx and compare this to, and we'll see in a second, that it's going to be always less than or equal to this. Because what I'm going to do now is I'm going to go ahead and label 1, 2, 3, 4, whoops, 4. Okay, so what we're doing now is we would be doing left endpoints for my Riemann sum. And this would be, of course, A1, A2, A3, A4, which corresponds to those A sub k's. And now in this case, my rectangles are overestimating the area under the curve. And so, well, let's go ahead and just write it down real quickly here. So if this series converges to a number, the integral is smaller and must converge. And then similarly, if this integral diverges to infinity, then the series has to the series is larger. I'll put is larger, so diverges. Alright, so that's going to be it for this video. The next video that we're going to have here for this section is just going to go through some examples using the integral test. Alright.